So in question 6, what we've got is we've got a person pushing a trolley. So let's suppose here's the trolley. And the person is applying a pushing force to it in order to move it through a distance of 22 metres. So this force is actually being applied a little bit into the ground. So at an angle of 29 degrees below horizontal. So I'll call this pushing force FP with a vector. And let's label that as being at a certain angle below the horizontal. So the person is not just pushing it horizontally, they're actually leaning on it a bit as they go along. Now that's not the only force which is acting on this trolley. There's also a frictional force which opposes the motion of the cart. So since I've supposed that the trolley is moving that way, the frictional force had better act in the opposite direction. And since it's opposing the motion, it's pointing in exactly the opposite direction to the way that it's going. Now we're told something about this friction force. We're told that that's 49 newtons. So we can just note that. So the magnitude of that friction force is 48 newtons. And also the angle that the person is pushing at is 29 degrees. And another thing that we're told is that the mass of this trolley is equal to 16 kilos. So I guess it must be empty. And what else? Well, we also have another force acting on this trolley. We have gravity acting straight down, so vertically straight down. And since the trolley is not falling into the earth, we also have a normal force, which is counteracting both gravity and also the person pushing the thing into the ground. And so we actually know what the magnitude of this gravitational force is here, because it's going to be equal to the mass of the trolley times by g. So we could also say that Fg is going to be equal to mg, since we know what that mass is. Now what this question would like us to figure out is what is the magnitude of the force that the person pushing the trolley exerts. Bearing in mind that this trolley is moving through this 22 metres at a constant velocity. So let's just note that trolley moves through a displacement. So it undergoes a displacement. I'll call that S, is equal to 22 metres at constant velocity. And what the constant velocity means is that the net force acting on this trolley has to be 0, because its acceleration is 0, so therefore the net force acting on it is 0. Therefore, these forces have to add up to 0. So probably the best way of going about answering this question to determine what force is necessary what force does the person have to apply in order to shift this trolley at constant velocity is probably to split these vectors up into x and y components and then say, well, if the total force on this trolley is 0, that means that the x component and the y component of that total velocity also have to be 0 as well. So a good thing to do would be to split these vectors up into their x and y components. So let me define what on earth I mean by x and y. Well, as normal, I just mean that x is going sort of horizontal and y is going sort of vertical. So if we split these vectors up, let's have a look at the friction force first. So the x component of this frictional force is going to be, because it's only pointing in the x direction, the magnitude of the x component of this force is just going to be equal to the magnitude of that vector. So that's going to just be 48 newtons. But because it's pointing in the negative x direction, we need to give it a little minus sign. And now the y component of the frictional force is just 0. The x component of the gravity force is going to be 0 because that's acting vertically. And the y component of the gravity force is going to be just equal to the magnitude because it's pointing in the y direction, but with a minus sign, so that's going to be minus m times g. And then let's have a look at the normal force. The x component of that is again 0, and the y component of the normal force, we don't really know. Don't know about that one. What about the person's pushing force? Well, we know that the x component of that one has got to be equal to, well, since we know what this angle is, let's complete this right-angled triangle. And then we can say that the magnitude of the x component is going to be equal to the adjacent side here. And the magnitude of the y component has got to be equal to the length of the opposite side. So here the x component is going to be equal to the magnitude of the person's pushing force, which is the very thing that we're trying to calculate, times by cos of theta. And the y component of that force is going to be minus fp times sine theta. Minus because it's pointing in the negative y direction. Now this is the thing that we're trying to figure out, and we know pretty much everything else in the x direction. So let's say that since velocity is constant, net force on trolley is 0. So that allows us to say that its x and y components are also 0. So let's figure out what the x component of the net force is. So this is equal to the x component of the friction force plus the x component of the gravity force plus the x component of the normal force plus the x component of the pushing force. And they've all got to add up to 0. The x component of the pushing force is just minus its magnitude. And we have 0 plus 0 for those two. And then we have plus fp times cos theta. And this looks like a pretty useful equation because we know what the magnitude of the friction force is, and we know what the angle the pushing force was being applied at, so we should just be able to solve this equation for the magnitude of that pushing force. And what we end up with is that that's equal to this. So now if we just divide both sides by cos of theta, we find that the magnitude of that pushing force is ff divided by cos theta. So that answers part A, and part B is to figure out the work being done by the pushing force. So work done by pushing force. So that is going to be equal to the component of the pushing force in the direction of the displacement. Times by the magnitude of the displacement. Now in this case, the trolley is going to be moving in the positive x direction, because that's the direction in which the person's pushing force is being applied. So the component of Fp in the direction of the displacement is just going to be the x component, this one. So then we can say that the work being done by the pushing force is equal to the x component of the pushing force multiplied by s. And that's equal to Fp times cos theta times s. But this pushing force we figured out was just equal to the magnitude of the friction force divided by cos theta, and then we just need to multiply by cos theta and multiply by s. We multiply by cos theta and divide by cos theta, and so we find that the work being done by the pushing force is just equal to the magnitude of the frictional force times the displacement through which the trolley moved. And now the work done by the frictional force that's equal to the component of the frictional force in the direction of the displacement. So again, the x component, so we're going to have ff x, and then multiplied by the displacement. Now we figured out that the x component was just minus ff, and then multiplied that by the displacement. So it's, in fact, the work being done by friction is exactly equal to the magnitude. So the work being done by friction is exactly equal to the work being done by the pushing force, but just with a minus sign. And then the work done by gravity so this is going to be equal to the x component of the gravity force multiplied by the displacement, which is just 0, because gravity is acting in the vertical direction. So gravity does no work at all on this trolley. Now I suppose we might as well just plug some numbers into this. So the force being supplied by the person then is just going to be 48 newtons divided by cos of 29, which gives us 54.9 newtons. The work being done by the person is equal to the pushing force times the distance, which was 22 meters. And so that gives us that the work being done by the person is 1,056 joules. The work being done by the frictional force is minus 1,056 joules. And of course, the work being done by gravity was just 0.